Hello again, I'm Nix, and today we are at the LeetCode website and we're going to solve the squares of a sorted array problem. I'm going to do this in the C++ language and go over the process from the planning stages to the actual code, all the way through the analysis of said code where we look at the time complexity and LeetCode rankings and all that. If that sounds interesting to you, then stay tuned. Welcome back. Now, the first part of the problem-solving process is the planning stage. This is where you make sure that you understand the problem being asked of you, you understand all of the constraints being imposed, so that everything is clear. Once you understand everything, you can start planning out how you're going to attack the problem. If you have not already tried to solve this problem yourself, I highly encourage you to do so, as it really helps to sharpen your coding skills. And then you can come back and watch the rest of the video to compare notes. Now let's get on into it, shall we? Given an integer array, nums, sorted in non-decreasing order, so it's either stays the same value or increases but never decreases. Return an array of the squares of each number sorted in that same non-decreasing order. So I can give you an example here, show you what the output is supposed to be, and an explanation. So after squaring this array, it becomes this array, where the negative values, after having been turned positive, mess everything up. And after sorting it, order is restored and everything is sunshine and rainbows. Woohoo! Let's see, constraints here. We're never given an empty array. There's a restriction as to how big the negative and the positive numbers are that we're working with. And as the problem stated, the array that we're given is already pre-sorted in a particular order. Okay. Now, as this statement here suggests, there is an answer to this problem that only requires a few lines of code. So I'm going to quickly put that up on screen, talk about it for a bit, and then we will get into more interesting territory here. And bam! There it is. As you can see, only 4 lines of code and you got your answer. You have a for loop here, you're iterating through the array, you're setting the value at a particular position you're at equal to itself times itself to square it. Once everything is squared, you're going to call the sort function that C++ has as part of its standard template library. You're going to iterate from the beginning of the array to the end of the array. Then you're going to return said array. Done and dusted. Very concise code, really easy to maintain it, highly readable, very cool. However, this follow-up question is intriguing. Can you find an O of n solution using a different approach? Now that requires me to explain a little bit about this sort function. The sort function that is available in the C++ template library is highly optimized one. It's really good. It's actually a hybrid algorithm and is a combination of several other algorithms. Merge sort, quick sort, etc. But this sort function has a time complexity of big O of n log n, which is worse than O of n. So what this is essentially saying is, can you square an array and sort it without using a sorting algorithm? You can iterate, you can loop through arrays, but you can't call a sorting algorithm because they all have time complexities that are worse than O of n. And that is going to be a challenge. Challenge accepted. Alright, how do you do that? Well, in order to figure out a plan of attack, a really good thing to do is try to key into various patterns that you notice when you're solving the problem yourself as a human being. What I keyed into is that when you square these values, here, the array still has some level of order still present. Depending on the section that you look at, it's either the same order or it's reversed order. In other words, if you look at the positive numbers, when you square them, they still have the non-decreasing order intact. But the negative values, when squared, have that order reversed. Instead of non-decreasing, they're non-increasing, where they're either staying the same value or getting smaller, but never getting larger. So, if I separate out those two portions into two different arrays and compare the smallest value that's present in each array to each other and add whatever is smallest to a new combination array, I'll be able to essentially sort through the array without calling a sorting algorithm. Does that make sense? No? Okay, I need my little helper to come in. Mr. Whiteboard, thank you. Let's go through an example to help clarify if you're still confused. So, Mr. Whiteboard, plop an example onto your screen, please. Thank you. So we have an array here. Let's square those values and give me two different arrays. One which will house all the squares of the negative values, and one which will house all the squares of the positive values. Thank you. Now going through this array, as I said, let's look at the positive one first. At the beginning of the array, going from left to right, we can see it is in non-decreasing order. They either have the same value here, or they get bigger, but they never go down. Great, so the smallest values are going to be at the beginning of the array. In the negative array here, I'm going to have the opposite situation. I'm going to have a non-decreasing order if I go through the array in reverse. So I start at the end of the array and go from right to left instead, ending up at the beginning or position index 0 of the array. Now, when I create the combination array, I want to check the smallest value that's present in the positive array and compare that to the smallest value present in the negative array. So here, I want to compare 0 to 1, which is smaller, 0. It goes into the combination array. And then I move that position to shift to look at the next value in line, in this case 1. I'm going to compare now 1 to 1, and in this case the values are the same, so it doesn't really matter which one I add, so I can just default to say adding the negative array value into the combination array. 1 goes there, and now I shift its position over to the left-hand side, shifting it over to 16. I compare 1 in the positive array to 16 in the negative array, and add 1, then add 4, then add 4, and then I eventually get to a point where the position has moved and I'm comparing 25 to 16. 16 is now smaller, it gets moved. I'm at the end of this array, but I still have to add the value of 25 into this combination array, and then I have my completed ordered combination array all nice and beautiful. Now, going through this example, this clues me into some resources I'm going to need for creating this algorithm and replicating this type of approach in code. What am I going to need? I'm going to need a positive array that holds the squares of the positive values present in the original array. I'm going to need a negative array, which houses the squares of the negative values present in the original array. And I'm going to need a combination array, which is going to house all of the values in the appropriate order that's going to be my final answer. I also, when going through these arrays, I needed to keep track of the position in each array that I was at. So I'm going to need to position integer variables. And I'm also going to need some type of looping mechanism that ping-pongs between the two arrays, comparing those values, and then adding whichever one is smaller to the combination array while modifying the position integers appropriately. Now let's dig into this while loop a little bit more. This while loop is going to have to be able to handle that ping-ponging capability, and it's also going to need to handle all of the scenarios that are shown on the handy-dandy whiteboard. And what do I mean by that? Well, let's say you create a while loop, and you say that the condition is while you're not at the end of the positive array. Now, these scenarios here, it may work for some of them, but that condition alone is not going to work for all of them. Cause look at scenario 1 here, where the negative array is smaller, the positive array is bigger, but yet the positive array finishes first. You get all the way to the end here, which is a 4, but you still have something in the negative array, just like this initial example. We had 25 still present when we got to the end of the negative array. In here, we have 16 present in the negative array, and we've iterated through to the end of the positive array. So that condition alone, that one while loop, is not going to be enough to complete the addition of every single value into the combination array. Now that's bad enough, but look what happens in scenario 3 with just this while condition. In here, you have the negative array being larger, the positive array being smaller, but in this case, the negative array finishes first. You get all the way to the beginning of this array, 4, and yet that is still smaller than the largest integer present in the positive array. So 4 gets added, you're at the end of the iteration through the negative array, but you still have your positive array present. So when you start a new loop and you iterate through to the end of that array, you're going to get a potential compiler error cropping up, where you either have gotten yourself into a situation where you're going beyond the beginning of the negative array, or you're in a situation where you might have gone past the end of the positive array, which is out of bounds, and the computer is going to be very upset and throw tons of errors at you. We need to avoid that. To avoid that, we're going to have to go through several loops. One while loop is going to have a condition where we're not at the end of the positive array and the negative array. Once we've gotten through one array completely, we'll have other loops that will exist to potentially finish off the other array if there's still stuff left in it, and always guarantee that we're never going to go out of bounds of one array or the other. Now, with that plan of attack here, I'm going to start going into stage 2 and start coding. First thing I'm going to do is comment out this section here, as you can see. Now, what I'm going to do first is start creating some of my needed variables. Okay, bringing you back, here are all of the vectors, the arrays that I'm going to have. I'm going to have a vector that's going to house the positive squares. I'm going to have a vector that's going to house the negative values that have been squared. And then my combination array that I've named sorted squares. Next, I'm going to fill the positive squared vector and the negative squared vector with the appropriate values. And to do that, I'm going to need a for loop. Okay, here is the for loop. As you can see, I'm also adding in some comments to help explain the various sections of code that I add. So here, this is a slight variation on the for loop. This is called a ranged for, which is just a more readable version where you can automatically loop through all of the individual items in a particular container. So I have an int variable here that I've called number, and for each of the items called numbers that are present in the vector nums, I want you to do stuff. If we have a number that is greater than or equal to 0, so positive numbers, then I want you to take the positive squares vector and add that number times itself. Here I use an else if. I could have also just used an else, but an else if is just a more specific way to do it. In this case, it doesn't matter whether this is an else if or an else. It's going to work either way. But I have else if number is less than 0, then I'm going to take the negative squares vector and push back that squared number. So that fills up all of those individual vectors with the specific sections of numbers that I want. Now I'm going to create some position integers. Okay, here are the position integers. And if you were wondering why I didn't create these after I created the vectors, this is the reason. The positive array index, the starting position I want for the positive array, is just going to be equal to 0. The negative array index, I need it to be equal to the end of the array. So for that to be set to the correct value, the negative squares array needs to have everything already in it and contain things before I set it equal to that. If I had this section here up above this loop instead, well, the negative squares size, because I didn't set it anything, I just declared it here and I didn't define it to be anything yet. It doesn't have anything present in the array, so its size is equal to 0, so this array index is just going to be set to -1, and I don't want that. So it's down here after the loop, so that stuff is present in the vector array, so that this index is set to the correct value. Moving on. Next up is going to be the while loops that handle the addition and the comparison for the combination array. Okay, here is the while loop with the condition that we need. And here, remember that we want to have this while loop happen while we are not at the end of the positive array and while we are not at the end of the negative array. In this case, we want to make sure that the positive array index, where our position is less than the size of the positive array, because we're iterating from left to right, from the starting index to the end index. And we want to make sure that we're also not at the end, in quotation marks, of the negative array index. But since we're iterating in reverse for that, we need to make sure that the negative array index, which starts at the end of the array and iterates from right to left, we want to make sure that is greater than or equal to 0. Now that we have that condition in place, we can start filling out the while loop, doing the comparisons of the values within each array. Here are those if statements. So I know there's a lot of text here, but bear with me. So this if statement here, what it's doing is the comparison. It's looking at the positive value here and seeing if it's less than the negative value. It's taking the positive array, looking at the positive array index position, and that value, is it going to be less than, look at the negative array at position negative array index and see if that value is greater than that value. If so, call the combination array and add the positive value to it since it's the smaller one. After that, increment up the index for that positive array to shift our position to the next one in line. Now, if this condition is not true, either the two values are the same or the negative value is the smaller one, we want to call our combination array and add in the negative value to it. Once we do that, we want to, in this case, decrement the negative array index, because for the negative array we're starting at the end of the index and working in reverse. Now I'm going to add the additional while loops that are going to come into play once we've gotten to the end of one array or the other and we still have the potential to add in more stuff, like so. This while loop is going to handle the scenarios where we've reached the end of the positive array, but there's still stuff present in the negative array to add. Now in that case, we don't have to do any comparisons because whatever is left in the negative array is already going to be, when added to the combination, in the correct order. So all we need to do is just add that value to it and then decrement the index value. This while loop is going to handle the scenario where we've reached the end of the negative array and we still have yet to get to the positive array. The positive array still has stuff in it, so we need to add said stuff to it and then increment the index for it. Okay, the final thing to do is to add the return statement, because this function here expects to have a vector returned. With the addition of this return value here, all of this code should be good to go. I'm going to add a little explanation statement here just to explain the purpose of these while loops. As you see here. This code, going over it, looks good. So, it is evaluation time. No compiler errors. Come on. None. Finished! Yay! Input. Answer. Those match. That's a good sign. No horrible, scary red text. So, let's do the full shebang. Pending. Judging. Accepted! Woohoo! Ah, it's always such a great feeling. Okay. Now, before we hit the button here, let's go on and officially start the third phase, the analysis phase. Now, this, you might have an idea for some reason or another already of the time complexity, but let's just verify that it's true. There was no sorting algorithm used, and I only have unnested for and while loops, which does indicate that it should be big O of n time complexity, where n is equal to the array size of the original array. And although there are 3 while loops here, all of them work in combination to go through the size of the original array once more. Now at this point in time, a question might be popping into your head saying, hey, this for loop goes through the array size n once. These while loops go through the array size n again. So wouldn't the time complexity be big O of 2n? Excellent question. Now, for time complexity, unless you're getting into the real nitty-gritty about it and analyzing in great detail the time complexity of your specific algorithm, usually for big O, you're focused on the general order of magnitude of it, whether it's big O of n, log n, big O of 1, big O of n squared, so on and so forth. So you usually have 2 rules that you're working by. 1, any constants that appear within the mathematical equation are ignored, and rule 2, you only keep the highest order term when thinking of big O. So whether you have big O of n, big O of 2n, big O of 5n divided by 6 plus 12, all of those numbers, 2, 4, 5, 6 plus 12, are constant. So all of them are dropped. And you only keep the highest order term here, which in this case is n. So all of those details essentially are brushed by the wayside. And this is indeed a big O of n solution. Now looking at this, and this is like bonus analysis time. This algorithm, yeah, it is big O of n, but looking at it in my mind, asking myself the question of, hey, where can I improve this algorithm? Where can I improve the space complexity or the time complexity? This is definitely not an optimized solution. It is somewhat optimized compared to, say, the 4-line answer that was using sort function. It's optimized in terms of time complexity here for large values of n. But there are still improvements that can be made. Off the top of my head, when looking at the algorithm that I made, I was thinking, can I do some things in place instead of having to allocate space and additional memory to make additional vectors? Can I eliminate some of the for loops in that case? Can I eliminate some of these while loops and handle some of these conditions all within the same thing and further optimize? Getting rid of some of the vectors I have to make and doing some things in place will optimize memory and optimize time complexity, because going from a single n from 2n is still a time complexity optimization, even though you're still in the same order of magnitude. That would be a great challenge for you to try as well. Consider that a follow-up to the follow-up. It's a cool, fun challenge, and because this video is already going to be extremely long, I'm going to leave a time where I go back to this problem and optimize it for a future video. Alright, with time complexity discussed, we are going to go ahead and see how LeetCode judges me. Okay. This distribution is interesting. Again, I take this with a heavy grain of salt because, as I said, even though LeetCode judges me as very high on the runtime, I know just from looking at the code, I knew from looking at it the very first time I came up with the algorithm, it's like, okay, there are definitely ways to make it better. But this distribution kind of indicates to me that even with kind of the grain of salt that you would take it with, it's probably indicating the two different solution types that you have, where this might be the solution that you use the sort function for, and then these solutions here are various O of n order magnitude solutions. Now, although I'm really high up here, I'm almost certainly extraordinarily low on the memory. Yeah, I don't even register on this one because there are ways to do an O of n solution that don't require several vectors. And as a final note here, if you're someone who created an algorithm that was similar to mine, here, here, and you got something that is an improvement in terms of time complexity compared to the, the sorting version here, but still not optimized, don't feel dejected by that. It's okay if, especially in a technical interview environment, if you don't come up with the optimal answer immediately. As long as you can demonstrate your problem-solving capabilities, that is what is really critical. Don't be dejected if you didn't instantly come up with the most optimal solution right off the bat. If that's where your mind went to immediately, awesome job, you're amazing. If you didn't, you're still awesome, okay? And if any senior software engineers see this and want to add in their opinions on this, I would love to hear from you. that was the squares of a sorted array problem. I hope you found something useful in this video, whether that be information, or if all I managed to do is make you smile when I said something goofy, I still consider that a win. Okay, happy coding everyone, and have a good day.